Professor Alessandro Saccon from Eindhoven University of Technology. And Alessandro is going to share his recent view of the reference spreading control and sensitivity analysis. Professor Alessandro Saccon is now leading or coordinating a EU project, Impact-Aware Control and Manipulation. I personally benefited a lot of and inspired a lot by his earlier works and exploitations. So let's see what he's going to present today. Alessandro?
Yeah, Yuchuan, thank you very much for the kind introduction. And also I want to thank you and up there for the invitation to present some of our works in this topic indeed. I think I want to start sharing my screen. Let's see if I manage to do that.
Yes, please.
So should be this window. So I think you should now see the PowerPoint window. Yes. And I think now if I make it full screen, then you should see everything.
Yes,
can you confirm?
It's perfect now. Yes, okay. I can confirm.
Okay, excellent. Right, so my talk is indeed about what is called the reference spreading control and sensitivity analysis. And then there's another part of the title, which is for robot trajectory with simultaneous impacts. And that's actually the focus on my talk. And I want to present at least my view, or one thing that we developed at UE in the last years that I think could be interesting for analyzing stability and controlling robots, making indeed a particular type of impacts that are not just located at a single point. Okay, let's see a bit of I have a general introduction here. So I'm talking about what we call impact-aware manipulation. And an example of this kind of a manipulation is the following. We are really skilled as humans to exploit collisions. This is also has been explaining in previous talk. And here, we don't fear collision, we exploit them, and this way we can actually be very fast. Here's a video of a few women, two women that are packaging products inside of tote boxes, and here a little bit more industrial, or at least more industrial context where somebody is using impacts to make the boxes slide or loading pallets and so on and so forth. I think there's also maybe others example. Here, we constantly use impacts essentially to speed up the motion. So the question is, how can we get robots doing these kind of things? Because this is not happening. And what is happening at the moment, and what is the state of the art, is of course that whenever we have, for example, to perform a peak, this is always static. So the robot might be super fast. Think of a delta robot, parallel robot. At the moment of making contact, the relative velocity between the end effector and the surface where the object is located is drawn to zero. And then when the object is picked up, then the velocity is again becoming larger and larger. So this is not ideal in terms of time and energy consumption, because in terms of energy, of course, we have always to decelerate and accelerate, but we know how to do it. Works wonderfully. I mean, there's all kind of examples in the industry that this is happening. But the thing is that humans don't do this, or at least human can do more. And what we can do is, for example, doing dynamic picking. Okay, I'm not the online situation. Maybe you can see me or not, but we can grasp objects, so we don't have to stop in the moment we make contact with the environments. We know what is going to happen. And for that reason, we also reduce the time for performing these kind of options. So we can reduce the time and energy consumption, but how to do this with the robot is not yet fully known. Of course, there are wonderful example things that are popping up in the last years. Things of Boston Dynamics, robots jumping and doing somersaults. So things are changing. The hardware is getting ready, and people are more and more investigating this possibility. And I'm telling you a bit of what we have been thinking within this context. So impact-aware robotics indeed is relevant. We can speed up and automate tasks, pick and place, assembly, packaging, parcel handling. For example, in logistics, maybe construction, could be interesting for all kind of robot configuration, a single arm, a mobile robot, or even a humanoid. Here you see also the robots that Yushan was talking about in his presentation. So you can make a robot climbing ladders very fast, or things like this could be interesting for maintenance or inspection. So in any case, what are the challenges? What is missing? Current practice, like I said, is really fast free motion, or maybe even fast contact motion. But then when you make establishing the contact, this is almost a zero or almost zero relative speed. And this is sort of limiting and restrictive. And why is this happening? I already mentioned, and I think people before me also mentioned this. There's a need for developing new frameworks for modeling, planning, learning, control, and estimation that includes impacts at their core. And this has to all at these levels, they have to be changed or extended with what we have. And so, my vision also is to create such a framework, and probably many others are having this idea in these days, also because the hardware is getting ready. And it would be nice then to show them the benefits of this kind of a technology on real system and relevant use cases. So problems, what are the things that are missing? One thing that I have here is, for example, validated impact models. So if you want to exploit impacts, you should figure out what happens when a robot make an impact with the environment. And so depending on the configuration, impact configuration, and pre-impact speed, you would like to have a prediction of where the robot will end up. Because if you cannot really predict what happens, as also in the presentations before me was said, if you cannot predict, it's very difficult to exploit impacts because there's no time really to react. So only most of the impact controls, in my opinion, is basically based on feed-forward. So at least there's not much time to do closed loop dynamics at the moment of impact. Maybe after an impact has occurred, maybe after 100 milliseconds, then you can start to react. But in any case, you need these kind of models. I'm not going to talk about this. There was a paper that we submitted at ICRA, has been accepted, that's sort of looking at this problem. What can we predict? How does an impact look like when you have, for example, a KUKA impacting a rigid surface? What can we predict this kind of behavior? When we make impacts with the environment, there are a lot of vibrations, and if we use a fully rigid body model, you don't see those vibrations. So what should you compare? Because for robot control, nobody's going to model all kind of flexibility you have in the drivetrain, or hoping to get very accurate models. Most of the time, also for robot control, what you use is rigid body dynamics. And maybe with some simplified impact models, like the one that was, like the ones that were presented in the previous presentation. So how can we compare reality with this simplified assumption? And when we have the simplified model, how we can use them? Okay. So in any case, let's assume that is sort of solved. Even if that is solved, then there's still issues, because if you have a reference trajectory, this is sort of a bouncing ball. You see in the left plot. Let me see if I can turn on my laser pointer. So imagine that this is time and there's a position, so just vertical position. Assuming that you have a control bouncing ball, so something that goes down back and forth, but you can also control the force in vertical direction. So if you see, velocity profile, you will see that these things will fall due to gravity. Then suddenly there will be a rebound, and so on and so forth. And now also the height is getting lower and lower because we assume that there's a bit of a dissipation at the impact time. So in this case, there's no input. So because, like I said, it's sort of an actuator. I imagine that there's an actuator going that can control the vertical direction of the ball. And this is just the reference. You want to start tracking this kind of reference. So you would like to put a controller. You start from somewhere else. And then at the moment you make an impact, well, the impact usually is not exactly where you want it. So if you use standard ideas of doing tracking, then you have a problem, because you had an impact. You would like to sort of start following the next reference, but if you have not a strategy that is aware of impact, what will happen is that it will try to follow again this reference trajectory and making the system impacting again, and so the performance will be extremely poor. So in the past years, we started in 2014, we developed something, a control theory framework that is called reference spreading, that is essentially doing this kind of thing. So we essentially propose to use not just one reference when tracking an impact trajectory, but having more than one, and switching between tracking one or the other, depending if a real impact has been detected. So if you apply this kind of technique, I'm not going to give many detail because I want to focus on something else in this presentation. But the idea is that whenever you detect an impact, then you start tracking another trajectory that is able then to make the system behave as you would expect. And so that this is black line is the same the trajectory that one would you would expect when having such a reference. The message here is essentially that by using essentially the same controller, is the same PDs, the same gains that you see in the middle plots, you get a way better performance just by changing the concept of error that you use for tracking. Okay, so by changing the definition of error, then you get better performance. Yeah, but this is not all. Yeah? So there's this time mismatch between the intended and actual impacts times. And so this is the reason why at least we developed this concept of reference spreading in the past. But then there's also another problem, that the kind of impacts we're interested are not just with a single point in general. Think of about, you have your box and you want to make an impact with a table. Yeah, then of course, the kind of impact that is happening here is happening on several points at the same time, ideally. And so, so imagine that you want you have a box, you want to make an impact with a table with a flat surface. So you want to keep during the impact a parallelism between the two surfaces. So what actually happens when you perform this kind of motion is that that will never happen. So you have an intention, you want to, for example, even think of a quadruped that is jumping, and maybe you have a reference trajectory where all the feet touches the ground at the same time. That is just maybe a motion planner is giving you that. And then you want to say, okay, now I want to execute this motion. Yeah, the chances that, for example, this quadruped would touch the floor at the same time, it will touch with the feet the floor at the same time is almost zero. And so what should the controller do in that case? There's somehow a gray area in between when the first foot strikes the ground and when all the feet are striking the ground, where you have to decide what to do and what should you send as a reference to the controller, the low-level controller. So that's the kind of thing that that also I like a bit to talk in this my presentation. So this is a sort of a simple animation of this concept. So imagine that you have a reference motion that is the blue one. So then it make impacts at the same time on the surface, and then another one which is a black one that makes contact first with the one corner. So if you look at what happens on the velocity x, y, theta and theta L, so those are essentially the position of the box and the position of this moving how to say, door, if you like, this green thing, then you'll see that the velocities, the reference, which is a blue link, just jump 1 times, while this perturbed trajectory jumps 2 times. So here you see the laser pointers. These are the 2 jumps I'm talking about. You first impact with one corner, then you impact with the second corner. So when the second impact has occurred, then you are sort of close again to your reference trajectory. But before, you have a strange kind of behavior. Think about the angular velocity of the box. If you just hit with one corner, then suddenly the velocity of the box becomes really high. So what should you do with feedback here? What should you, so simultaneous impacts are something different than the single impact. And there's the need also to try to create control strategy that have some guarantee of stability. There's the need to further develop even the theoretical aspects, how to analyze this kind of trajectory. And this is actually what I want to talk today. So there's not going to be much experimental work, but I want to convey, at least to show you one of the tools that we developed to try to analyze locally the behavior of this kind of trajectories. Then there are many other problems in impact-aware robotics or impact-aware manipulation. So you need also to have perception. So has the impact happened? Did it go as expected? So on and so forth. You need to have also particular kind of motion planner. And then this is also one of the questions that I heard from the audience a few minutes ago. Okay, what is the best pre-impact speed and posture for a certain desired task? You have to lift up a box that is heavy. Okay, the result of the impact really depends on the configuration, so the posture. So it's very important that you can can optimize for that. Yeah, you can do all kind of learning. Learning even now is done with the assumption that the contact transition are occurring at zero speed. So when you have demonstrations where the robot is actually impacting, what should you learn? How you should store the reference trajectory or dynamical system, for example, that describe that motion, especially with the situation of simultaneous impacts. And in any case, then you need software that allows you to do all this and make it happen on real robots. So the good starting point is that suitable robot hardware is becoming available. It's still too fragile sometimes. Yeah, maybe a little bit too stiff. There should be work in trying to make it more compliant and with less vibration. But there has been definitely an increase amount of research and there are more and more robots available in the last decade that is suitable for this kind of tasks. But at the same time, yeah, we need also to improve, if you like, the nervous system. So a theoretical framework and then in implementation and software, these kind of ideas. So for today's presentation, this is what I'm really want to focus is this time mismatch between intended actual impact times as well as this practical unlikeliness of achieving desired simultaneous impacts. And so and then what I want to present is how we are thinking of then locally studying this kind of trajectory. And this local study can then be used, for example, for motion planning, for control, and so on and so forth. So in particular, what I want to discuss about is one concept, which is what we call a positive homogenization of this hybrid dynamics. So don't get scared by the name, but think of a positive homogenization as a sort of a concept like a linearization. So if you have a dynamical system, you have a particular trajectory, you can linearize that dynamics about a trajectory, and then everybody's familiar with that concept. So it's like if you have x dot is equal to fxu, then this linearization will be something like z dot is equal to a z plus bu, with a and b somehow derivatives of the vector field along a given trajectory. So the point is that can we do something like this for system with simultaneous impacts? So just to show you what this positive harmonization allows to do, I have a small video here. But the message I want to convey is that we are really focusing on intended motions with simultaneous inelastic impacts. And these type of motions are also, I think, the ones that we experience the most as humans. So if I give you a pen and I let it drop on a table, yeah, there will be rebounds. The likelihood that you can really predict what is going to happen exactly on the pen at the moment of impact is almost zero. So it's really unpredictable. It really depends on the particular contact point that strikes the floor first. But if you then think about the palm of your hand and you hit a surface with that, then you realize that more or less, you don't really know which finger has touched the surface before, but more or less the result is always the same at the end. Okay, so there's something special about this inelastic impact. It's actually you need to add more assumptions. That inelasticity together with simultaneous impact is making things easier to predict and also to analyze. So these are really the kind of motion and trajectory we're interested in. And for those type of trajectory, we can say something, at least locally. Okay, let me see. This is a video that there was a paper that also was part of a work of a previous PhD of mine. So let's see. This is a similar things that you saw before. Let me start again. So you have a reference trajectory. This robot is making impact very quickly with this moving table. Okay, so that's the motion, and it's simultaneous because it's a flat surface. So we're not impacting just on one corner, but a really flat to flat surface. So here there's a slowdown motion here shown, and you see it again. It's just, you see, it's very parallel. Okay, so one single impact. So if you perturb the trajectory I was telling you before, then you see that there are two impacts now. You should look at the plot on the right. I hope you saw it. I think it's nice to show it again. Over here, let's see. Yes, so if you look at the right, then because there are certain uncertainty, you don't really know where the plate is. Yeah, this is what you will experience, two impacts. Okay, and what we ask ourselves is that, can we still create something like a linearization? So I want to linearize the dynamics about my reference trajectory. So this plot requires a bit of or this video requires a bit of an explanation, but I want to give you the intuitive message here, because the mathematics is quite involved. I'm not going to talk about that or even try to explain in half an hour. But let's go back. So what you see on the right is this perturbed trajectory, and what you see on the left is what we call this positive homogenization of this reference trajectory. So what you see here is the superposition of the reference trajectory with another dynamical system, which is this positive homogenization that I will give you a bit of detail later, that it is somehow unphysical, but has a nice property that it is essentially a first order approximation of the real perturbed trajectory. So what happens here is that this positive homogenization system has only one impact. It's what you observe physically is very weird, because now there's a compenetration. So the two trajectories, the perturbed and positive homogenization, are very similar. At the moment when you start having impacts, then the perturbed trajectory is doing what physics is saying. This positive homogenization is doing something weird, and then this is jumping actually at the moment where the reference was jumping. But the point is that after the whole train of intermediate impacts has occurred in the perturbed trajectory, then the positive homogenization give you back again a good approximation of what the system is doing after the whole train of impact. So here's a picture to try to explain what I'm doing here. So let's look at the reference trajectory, the nominal trajectory. So imagine you have this trajectory with certain impacts, free motion, simultaneous impacts, then some motion, then maybe detachment, and then you move again, and then another simultaneous impact, so on and so forth. Now, yeah, you take this blue one is only one impact, simultaneous. Then you perturb your system, and then, like I said, yeah, you're not going to have only one impact. You have multiple. You don't even have the sequence. You don't know how many. If you have a planar situation, this will be 2. If you are in the plane, in the space, then for a box you will have 3 sometimes. Think of putting down a box. You can first hit on a corner, then on a side, and then the whole surface. But you don't really know the order. You don't really know how many of these. So what we develop is this green line. This green line starts exactly as the perturbed one. But what it does, it's a strange thing that it continues until the nominal time you had. It jumps at the nominal time. And the point is that at the moment where this perturbed trajectory finally is in the expected contact mode, then it's still a good approximation of the trajectory. This means that if I know the initial condition, I can predict what is going to happen to the perturbed situation, even if I don't know exactly all the little intermediate impacts that I have. And so I can do, for example, optimization if I'm interested in looking at the whole trajectory by using this tool. That's more or less the message. And also when looking at stability, at the end, if this is a periodic or non-periodic, I can only look at what is happening at the end and see if that, for example, is getting smaller and smaller over time, so I have stability. I'm not really interested in understanding which particular order impacts occurred. So that's the message. So some details. I don't think I'm going to go into the whole explanation, because again, this is really detailed, but the point is that if you have some familiarity with the hybrid time, the hybrid system, then you know that people has developed this concept of continuous time and discrete time, TJ. For this analysis, for developing this, we had to create another concept, which is called multi-scale hybrid time. So we are interested in continuous time. We are interested in macro, what we call a macro count or macro discrete times that just defines essentially, oh, now I'm in free motion, now I'm in contact. And then we also have a micro counter K, which is sort of counting how many intermediate impacts occurred. So the reference trajectory, for example, will only have one micro counter, so only one advancement, and then the macro counter will again. But for the perturbed trajectory, this K will be different depending on the initial condition. Sometimes you have K only one, sometimes you have K going 1, 2, 3. But the thing is that from a reference perspective, from a task perspective, the only things you care is the first and second index here, and the K is just used for the analysis. And this plot is just showing again the fact that you have a simultaneous impact. So there are two constraints activated at the same time nominally, and then you jump to the post-impact state. And if you perturb, then sometimes you impact first one constraint, then you go into an intermediate mode, then you hit the other constraint, and then you finally get to the same contact state. But if you change the initial conditions, then you could hit first with another corner of the box and go in another intermediate contact state, and then when the other corner of the box impact the surface, then you're back on the same contact state. So somehow we are always interested in looking at this situation, and here we don't really care what is this intermediate. So that's exactly why we are developing this analysis that allows you to just focus on what happens before and what happened at the end. And we have this positive homogenization of the dynamics that allows you to approximate this behavior here and here without sort of caring on what happens in between. Okay, so by the way, this multi-scale hybrid time, I don't want to claim that we invented it, because there are also other works, in particular one from 2010 of Moraresco and Brogliato, where they use similar concept for defining, for example, controllers. But this positive homogenization that I'm discussing is something new that we introduced a few years back. Yeah, so what can you do when you have only a single impact? So we call it single jump flow system. So only one impact. To think of a robot impacting with a spherical end effector with the planar surface. So the plane and the surface impact only one point. And that is something that we already shown that you can approximate locally behavior with a linear system before a jump that jumps at the nominal time of the trajectory, and then another system later on. Okay, so this is a standard things. By the way, this is not fully new in the robotics community. Here is actually a little bit of the details about this jump gain that I was describing. So when you linearize the dynamics, there's something that depends on the derivative of the jump map here. And as well as a term that takes into account the time mismatch of the first order. So if you're familiar with the work of Katja Mombauer in 2001, for example, open loop stability of robot running, and you will see that these kind of formulas are there for optimization and study stability. And it's interesting that you take a system where the jump is state triggered. So a jump occurs only when you touch the surface, but you can still get a system that where the jumps occur at the nominal impact time. So that's something that takes time to understand. So this tau here is the nominal impact time. So this jump map is a strange thing that has both the linearization of the jump map, but also has another part here that takes into account an estimation, a first order estimation of the time mismatch, but it's based on the state. So like I said, I hope you have some familiarity. If not, I suggest you to read, for example, thesis of also Katja, or also the PhD thesis of my student Mark Reining in 2019, where these kind of things are explained. So now, like I was saying, the dynamics, you can think of it as the robot is moving in free motion, then an impact occurs because the robot touches the surface, and then the state is reset. Okay, and the condition where when when this reset happens, whenever indeed you touch the surface. So you imagine that there's a function, maybe gamma here, at least theoretically, that gamma describe the distance between the robot and the surface, and at the moment of making contact, that function is 0. Right, so this is an illustration of the time trigger linearization. So you have a reference trajectory, you jump on the nominal time, then you perturb the trajectory, the jump will occur at a different time. And what this time trigger linearization is doing, and again, this is relatively known, then you can actually approximate this blue curve with the curve that is this red one that still jumps at the nominal time. You see, the thing is that the blue and the red are really close, and if you truncate this here, and then you actually integrate backward this red curve, the linearization at the actual impact time, the blue and the red curve are first order approximation of each other. Okay, so they can be used for doing optimization or studying local stability with the linear theory. But what we've done in the recent years, and that's exactly what I wanted to just convey as a message, is that we moved from we were able to extend this kind of thinking to inelastic simultaneous impact. So we go from this type of linearization where you say, hey, I have a linear time varying system, which is linearization about the trajectory, the reference trajectory as a function of time. Then there's a jump at the nominal time, and then I continue. Now we figure out that we can do the same things also with an elastic simultaneous impacts, but we have to change the impact map. And this impact map is not more, it cannot be linear. That's our surprise, that what we found, it cannot be linear, it has to be positive homogeneous. And positive homogeneous means that essentially if I take this map and I evaluate, instead of on the z, I evaluate on a lambda times z, where lambda is a scalar, as long as the lambda is positive, then I can say that the result is going to be lambda times the same function evaluated to z. But it's not linear, because if lambda is not positive, that is not true anymore. So linearity has this property that, okay, you can sum two things up because the scalar you put in from, the sign doesn't matter. Positive homogeneous is not enough. It has some property of linearity, but it's not fully linear. So, but still, it's a first order approximation of the dynamics. I understand that this can be a bit overwhelming if you never saw this, but the message here is that we can do a local analysis also with inelastic simultaneous impacts. Here's a formula. When you have only two impacts, then the nice thing is that this impact map, this positive homogenization is constructive. So if you have the robot dynamics, multi-body dynamics, you have the surface, you have all these quantities, you just write a software and you can compute all those kind of things. So again, too many things, too many details. I don't have the time. It's too complicated to explain now. But the thing is that essentially you see that this positive homogeneous jump map is something like a gain times z. So it's sort of linear, but because it also depends on z here, that's actually what makes it positive homogeneous. And essentially what's happening is that you need to have a different gain for different region in the state space. This is what we're saying. So essentially you need to, in this case, you have to enumerate all possibilities of impacts. So the first impact happening before, or so first corner, and then second corner, or second corner, first corner. But so you can do all this analysis, and you end up with this kind of a map. So what I was saying is that, yeah, it's a first order approximation. That's the key result. That if you take, for example, the difference between the nominal trajectory alpha and the perturbed one, the real one, the one with state trigger jumps with simultaneous impacts, and you evaluate, for example, at t equal 2 seconds, that is after the whole trajectory has occurred, then you get this blue curve. that you see here in solid, and it's of course non-linear. And here is epsilon is the amount of perturbation in the initial condition you put in. The thing is that, yeah, the positive homogenization, this Z, it has the same behavior for small epsilon, and then of course you see higher order terms popping up. But the thing is that, yeah, you have now an approximation away from this impact that is first order. I want to give you a bit of further detail, and maybe I'm also asking you, Sean, to understand how much time do I have. Maybe it's I'm almost finished, I think. So, are you listening to me, Yukon?
Oh yes, sorry. I was just replying a message. Yes, basically you have time until 20, so you have 5 minutes.
5 minutes, okay, I'm really close. Yeah, thanks.
Yeah.
So then, so we have certain assumptions. So I was saying inelastic impacts. It actually is not enough. So you need to have inelastic impacts that were essentially always make the system reach the same nominal post-impact mode. So if you think of holding a box, then when you impact with the box the table, yeah, it's true. You don't know exactly the sequence, but you know that the box will in the end end up with the whole face in contact with the table. And also, whenever a jump has occurred, yeah, then that corresponding constraint should remain active until reaching the nominal post-impact mode. And if you want a little bit of intuition, or at least when does this happen? Yeah, this is a situation where you can look at what is called the constraint angle of a simultaneous inelastic impact. So this is a concept that is defined in general, but think of, for example, on the planar situation where you have a point mass that is impacting a corner and where the impact is inelastic. Of course, if you impact the corner here with this ball, because it's an elastic, you will get stuck there. And if imagine what happens when you perturb a little bit the position and velocity of this ball, well, then you will impact and you will start sliding, and then you will get stuck to the corner. But if the angle between these two surfaces is not 90 degrees, is larger, then when you impact, yeah, and you will start sliding, but the moment you start impacting the other wall, then you'll start sliding on the other surface. So it's very important whenever you have this inelastic impact also to consider what is the angle. And again, this angle is defined in general. It really depends on the mass matrix at the impact moment and the type of constraint you have. But what I'm talking about in this talk, I'm focusing on this situation, not on this. So the theory I'm defining applies to this, which is, for example, what happens when you have a box that is held by the hand of a robot, and then yeah, this box is for example not smashed, but it made impact the table. So, but at least I wanted to give this message here. And conclusions, yeah. So I provided an introduction to essentially yeah, TOE efforts to extend this sensitivity analysis for hybrid system from single jump flow trajectory to simultaneous jump flow trajectories. And the key message is really that we develop this concept of positive homogenization that allows to analyze the local closed loop behavior, even open loop, if you like, of a robotic system undergoing intentional simultaneous and inelastic impacts with this bounded constraint angle. So don't think that it for all situations. And the point is that this positive homogenization can provide also a key component to develop, for example, iterative optimization algorithm. If you have gradient-like methods, yeah, you can use these kind of tools to find the descent direction. And I'm really interested to explore this kind of tools for motion planning of robotic systems, for example. And yeah, on this, I would like to conclude and thank you all for your attention.
Thank you very much, Alessandro. Yeah, very nice presentation. and very impressive work. Indeed, that we are going to benefit a lot from the hybrid control approaches